Here's a quick tutorial on how to use what we call Spartan Student. Spartan Student is a molecular modeling software that you can find in the Carabine lab. The version that I'm using is slightly different, but should be identically the same. So if you're in the Carabine lab, go ahead and go down to the lower Windows 10 icon, and then you should see Spartan Student either in the chemistry department applications or by itself. And then you can go ahead and open it up. You'll see a screen that looks like this. So this is our graphical interface that we're going to use to draw molecules with. If I have a brand new molecule, I'm going to go ahead and go over here to File, and let's do a new build. Okay, so if we want to do a new build, that's also this icon. So if we come over here to the right hand side, we see that we have a number of what they call model kits. We have basically the starter kit for organic. We've got an sp3 hybridized carbon, sp2, sp. We've got a delocalized, and then we have a number of elements. We also have down here groups. So if I click on the groups, I could have an alkenyl, and then over here, these are all the different groups that I could put in that are already pre-built for us. I could also go to the rings, and so if I click in the rings, I'll see benzene, and then I'll also see a whole series cyclopropane. Cyclohexane will be the one that we'll use for our case studies. So if you click on, for instance, cyclohexane, whatever's in this box will then automatically show up in terms of when we click in this green area. So before we do a cyclohexane, let's just go back and look. So for instance, here's an sp3 hybridized carbon, and again, I have all these choices. These are the same choices that are in this box. Now, this inorganic button gives me some flexibility to draw atoms that I normally wouldn't be able to draw. And you're going to need to use this for the bromonium ion. So you have the ability to choose your element along with the geometry that you would like. If you want to draw a trigonal bipyramidal carbon, you can do that here. The calculation will blow up on you, but you can still draw, a tetrahedral carbon. You can draw the trigonal bipyramidal. And so, for instance, if I wanted, later on, I'm going to want to have a bromine with 2 bonds. So in order to do that, I'm going to go to the periodic table and say, okay, choose a bromine. And then I'm going to choose it with a bent structure so that when I come over here, I now have a bromine with 2 bonds, whereas in the organic sort of basic kit, I only have a bromine with 1 bond. Okay. If I draw an atom I do not want, let's hit the delete button and we can delete it back out again. So let's draw something simple like a butane. That's the case study, or that's how it describes how we determine the equilibrium constant between different conformations. So let's also look. I'll just show you some other ideas here. You can go into the peptide realm, and you can actually choose a series of amino acids. If you wanted to make a protein, it will put all of them together in an alpha helix or a beta sheet, and so you can actually use that. If you wanted your nucleotides to draw a piece of DNA, you could do that as well. You could draw the strand by typing in a sequence, and then you can, if it say DNA single strand, it'll give you the single strand. If you have the double strand, it'll automatically put the complementary strand on it. If you want a DNA RNA, it'll make that conversion for you. So you can actually draw in with that software a piece of DNA or a piece of RNA. And substituent, I'm not sure what substituent does. Substituent apparently gives you the ability to just put an aromatic group in, or a generic OR group, methoxys. Apparently you can put in different groups. I have not used this. Here's your list of electron donating groups that you could use, or here's a list of electron withdrawing groups. That might be useful if we were going to do studies of, for instance, the electron. Let's say we were going to do a study of how the electron density within the benzene ring varied with the number of electron withdrawing groups. I could just create a whole series of molecules by using the aromatic ring and then using the electron withdrawing groups one at a time. Honestly, I haven't used that yet. So let's go back to the simple model and let's build ourselves a butane. So we're going to go to sp3 carbon. I'm going to click here. All of the yellow valencies are places I can now add atoms. So I can add my second, I could add my third, and I could add my fourth. And so what I've done here is I've drawn a zigzag structure for butane. Once I've drawn it, I can go to this pair of glasses which says view, and now all the yellow positions will become hydrogens. A couple things in terms of manipulating the molecule. If you hold down on the left mouse key, you can go ahead and rotate the molecule this around. If you use the right mouse key, you can slide it across the screen. If you use a control left mouse key, you rotate it because control left mouse key doesn't do anything. How about control right mouse key? Okay, that doesn't do anything either. How about shift? The shift left mouse key lets you rotate it in the Z plane. So we can rotate it this way. We can slide it back and forth. If you want to get it larger, that's where you hold the control key down and then move your mouse. Let's see. Nope, sorry. Shift right mouse key. And then if you kind of move it up into the corner, it gets bigger. Shift right mouse key. You can make the molecule smaller. Okay, so those are our basic manipulations. If you don't like this ball and stick model, you can come over here to the model button and you have a lot of choices. You could make it tubes. Sometimes I like tubes because they're easier to see. You could also make it, again, our ball and spoke. Then you can also go to a space filling model where you can actually then see what the real van der Waals radius of the atoms would look like. And so that's sometimes helpful to see what the true shape is. And we'll probably need that if we're going to look at some steric interactions. So there's also other things you can do. Once you get into the biomolecules, you can actually insert ribbons within your structure, or you can give it labels. You can remove the hydrogens from the system by clicking there. You can click back and it'll give you the hydrogens. So let's go back to our ball and spoke. So the first thing that we would want to do is, let's do as an example, let's calculate the energies of the two staggered and butane conformations looking down the C2 C3 bond. So if we orient the molecule, and this is where the shift left hand comes into play, because now I can rotate it. Here's our Newman projection. Methyl group up front, hydrogen on the hydrogen, two hydrogens on the front carbon, hydrogen on the back carbon along with the methyl group. Again, if you don't like that, you can always go to tubes. That might make it a little bit easier to see. Okay, so here's my Newman projection. This is for the what conformation? The anti-conformation. So let's calculate the energy of this molecule. So we have a number of different types of calculations that we can do. I have more on this version of the software than's in the Carabine lab, but what's in the Carabine lab is more than most students would ever use. Let's go to setup the calculation, and when we go to setup calculation, we have this screen. So we can choose a lot of different things here. We can do an equilibrium geometry. We could do an energy of just this conformation. If we do an equilibrium geometry, then what will happen is that the molecule will start moving the atoms around until it finds the lowest energy conformation. We can also do, with a little bit of knowledge, some transition state modeling, so we can determine the transition state of a reaction. We can look at the distribution between the conformers, and then we can do an energy profile. There's a lot of things we can do here. We're today just going to do equilibrium geometry. So we're going to do equilibrium geometry in the ground state, and all calculations are done in the gas phase, and that's kind of a limitation. We do have the ability, at least in my software, to be able to simulate it in a nonpolar and a polar solvent, but we're just going to stay in the gas phase. What method are we going to use? Well, we have a number of methods. We have molecular mechanics, which is the simplest method. That is all parameterized. So if you have a bond, or if you have a molecule that's not been made, or there's no parameters for it, you can't use molecular mechanics. It's the simplest and the least computational, having the least computational input required. Next is semi-empirical, which is half calculations, meaning half of using the Schrodinger equation and half using parameterization. Hartree-Fock gets you to using mostly, if not all, of the Schrodinger equation, and then density functional theories come into relevance because it's a higher level calculation. Today we're going to do everything with semi-empirical, and then we have what kind of parameterization do we want. We have AM1, RM1, PM3, PM6, and MNDO. Personally, I like PM3. And again, if you were to study computational chemistry, you'd learn about the pluses and minuses of each one of those. AM1 is typically used for organic molecules. I like PM3. It has lithium and some other things in it that I've used in the past. So we're going to do an equilibrium geometry in the gas phase, semi-empirical methods using PM3. Now, this box over here you have to be aware of, because right now we're going to do a neutral molecule. If I wanted to do a cation, I would need to come over here and say it's +1, or if I was to do an anion, I would have to have it -1. If we don't have the correct charge for the molecule, the calculation will basically blow up on us, and it'll tell us it couldn't do it. All right, so now we've got our setup. We're going to do an equilibrium geometry. I'm going to go ahead and submit that. When I submit it, notice that it gave me a name. It says it's N-butane. Okay, but I'm going to add something to this and say it was N-butane the anti-conformation, and now I'm going to go ahead and say save, and now it's going and starting the calculation. And when the calculation is finished, when it's found the lowest energy state, which it just did, it then gives me the result. You have no idea how fast that was with a fairly inexpensive computer. There were times when this might take an hour using old computer systems. All right, so it didn't make much change, but what's important now is I can get the energy of this molecule. So I come up here to my display, and let's display the output. And so when I display the output, I get a summary that may or may not look like yours, because I think this one's a little different. But I can go to the display the output, and then it would give me all of this information that I may or may not want to use. Actually, I'm going to get out of this and we're going to say display properties. So this is actually a better screen to look at. So in my screen here, I see all sorts of things. I see what its energy was. I see what its HOMO and LUMO energies are. I see its dipole moment is 0, which means it's a nonpolar molecule. It has no tautomers. There are 3 conformations of this that it has. I could do some more calculations on that. If I want to go to thermodynamics, I could actually calculate some of these values, which I don't want to do. And QSR, that's if I wanted to look at some structure reactivity information. I don't want to do that. What's most important to me is the energy. So the energy of this molecule then was calculated to be minus 121.2 minus 121.60 kilojoules per mole. So the anti-conformation is minus 121.60 kilojoules per mole. Okay? Now, what you need to remember with these energies is the more negative the energy, the more stable the molecule. In other words, the lower the number, and when they're negative, the more negative the number is, the more stable the molecule is. So great, we've done anti. I'm going to come back here. I'm going to go ahead and save that. And now what I'd like to do is now I'd like to create the gauche form of this molecule. And without making a new one, let's go to the edit, our new build. And so if I click on that, wait, I shouldn't have done that. Let's close the let's close this molecule out. If we don't close the molecule out, we're going to end up with multiple molecules on the screen, and we're going to confuse ourselves to no end. So now let's do a new build. Okay, so we got no molecules. Let's go ahead and build a new butane, 1, 2. Now, let's build off these 2 carbons the gauche. So on the front carbon, I'll put the methyl group there. On the back carbon, I'll put the methyl group there. And then if I go to my glasses, I've now built my gauche. So here's the gauche form of butane. Great. Let's go ahead and now set up a calculation for this. So I'm going to go ahead and set up the calculation, the same one that I did before. Equilibrium at the ground state. In the gas phase, I'm going to go back here and do semi-empirical PM3. The molecule is still neutral, so everything's good. Now I can go ahead and say submit. Now I'm going to submit this as N-butane gauche. Save. Okay, and so now it's going to go ahead and do the calculation, and it'll come back with that molecule. You can see it's now in the gauche conformation. This is the lowest energy. If you're wondering why it didn't go all the way down to the anti, because we know the anti is the most stable form, in order for the methyl group to have gone all the way down to anti, it would have actually had to go over a barrier of the eclipsed form. And these calculations are set up so that they don't, when they encounter a barrier, they just go back down to the lowest energy. And that can be a problem with these calculations. So here's my gauche. Let's display the properties. And so what was its energy? Its energy was minus, for gauche, minus 119.43 kilojoules per mole. And so this gauche is less stable than anti. There was minus 121. If I take the difference between those 2 molecules of the 121 minus the 119, that's going to be minus 2.0 2.17 kilojoules per mole is the net difference between those two molecules. And so the question then is, for these two, for the gauche, for the anti, that 2 kilojoule per mole difference, what would that mean in terms of an equilibrium constant? And what would that mean in terms of the percentages of the molecules that are gauche and anti? And in your handout, it leads you through that calculation to figure out what the percentages are. So this is how we make our molecules and how we can run our calculations. A couple things that we can do with this that we won't necessarily do in these case studies, but if you were to do modeling, you could do some more of this. Let's edit this molecule. So we can say, let's close this and save it. Let's do a new build. So one of the things we could do is we could do a new build with, we could do it with carbonyl. So let's take a methyl group and click there. And then let's get a carbonyl. And let's put the carbonyl there. Now you'll see there's a double bond that we have to come over here to double bonded oxygen and put that in place. And then maybe we put a methyl group here. So here's acetone. Now, one of the things you see in your textbook quite often, if you're using your textbook, is you'll see a color coding of where the negative and positive charges are in the molecule. So let's do a quick calculation here. Equilibrium with PM3, and let's go ahead and submit that. Come on, it'll tell me it's acetone because it actually knows the IUPAC naming. I'm going to go ahead and save that, and it should be a few seconds for it to do the calculation. Boom, it's done. So there's my acetone molecule. Now, one of the nice things I can do about this is I can still go up and look at my properties. So my properties will now say that it has this energy. Now it has a dipole moment. And actually, if I come down here to this button, it will show me the dipole moment in the molecule. And it's going exactly where you thought it would be in general chemistry. So what I'd really like to see is where the positive and negative charges are. So I'll take away the dipole moment for now. Let's display a surface. So these are always fun to display the surfaces of the different molecules. So we go to display surfaces, we get this. So now we can add some different surfaces. You'll in PChem, if you were to go on and take it, you'd learn more about the highest occupied molecular orbital and the lowest unoccupied molecular orbital. But we could go to density. What would a density plot look like? It looks like that. Well, that's actually just the plot of the molecule with its electron clouds in place. And since the molecule isn't color-coded in real life, it would just be this gray blob. But there's the shape of the molecule. All right, densities are pretty boring. Let's go to an electrostatic potential map. So if I click on that, now we can see the shading. So we can see that red is delta minus and blue is delta positive. So what we have is we have the delta minus carbonyl, and then we have the carbon of the carbonyl is now the delta positive. One of the things I like to do with these is you can get these solid models, or if you click on the model, you can come down here to this corner and say, I'd like to see it in mesh, or I'd like to see it in dots, which I never want to see, or we could do it with a transparent, so that now I can see the molecule and where the delta positive and delta minus charges are. And this might be really helpful if I had a large molecule and I needed to know, well, where's the delta positive charge for the nucleophiles to add to? Where's the delta negative charge where the electrophiles might add to? And well, let's just, for the sake of argument here, let's change this molecule up a little bit. Let's see, we've got to make it back to solid. And then you have to display the surfaces in order to turn them off. Okay, so that's how we can draw the molecules, and that's how we can calculate their energies. So that's what you're going to do for the few case studies that we have given you for this week. And so when you do those, write down your structures, any features, you know, kind of sketch out. There's no need to really print out any of these structures. You could if necessary, but probably just sketching them out on the piece of paper would be good. And so that's what we're going to do this week as far as the computational part of this in the Carabine lab.